Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we shall start with the actual vapor compression cycle. In this lecture we will be depicting actual refrigeration cycle on TS diagram, and we will transfer these cycles on pressure enthalpy diagram as well, and we will take work example in this case. Now, as we know, on a temperature entropy diagram, so far we have analyzed a vapor compression cycle operating between two temperatures T1 and T2, and the vapor is saturated after the compression. It means the vapor which is coming from the evaporator and entering the compressor is wet vapor. In actual practice, this situation is avoided. This situation is avoided because if the wet vapor enters the compressor, it will carry itself droplets of the liquid, and these liquid droplets, first of all, they will damage the compressor valves. Secondly, they may wash away also the lubricant in the compressor. So, this situation is always avoided. It is always ensured that the vapor which is in actual cycle, the vapor which is entering the compressor is either saturated or it is superheated. So, this state, let us say A, B, C, D. So, this state A will be shifted here, and when the compression takes place from A to B, definitely after the compression the vapor will become superheated. This superheated vapor emerging from the compressor, first of all it will be desuperheated in the condenser. So, temperature at B is greater than temperature at, let us say, E. Temperature at E, though desuperheating of vapor takes place, and after desuperheating the condensation of vapor takes place inside a condenser, and we attain state C. At state C, there is constant enthalpy expansion or throttling of the vapor, and again it enters the evaporator and evaporation takes place. This is x is equal to 0 and x is equal to 1. Now, in this case also it is very difficult to ensure that the vapor which is entering the compressor is dry and saturated, because exactly attaining this property is difficult. So, normally the vapor is superheated in a range of 2 to 5 degrees centigrade when it enters the compressor. So, instead of point A here, the point A is shifted. Point A, this is T2, this is T1. So, point A is shifted, and the vapor which is entering the compressor is at temperature A dash, and temperature as A dash is greater than the temperature at A, and from here the compression takes place and we attain temperature B dash, the state B dash. Now, you can see here that as we keep on heating the vapor, so compression work was minimum when we were compressing the vapor from this point to this point. When we are compressing the vapor which is saturated, the compression work increased, and when the vapor is superheated, compression work further increased. This is temperature and this is entropy. And at the same time you can see when we are shifting towards the right, it means when the vapor which is entering the compressor is saturated, the refrigeration effect is also increased. The vapor is further superheated, which also increase the refrigerating effect. At the same time the compression work is also increased. So, there are two possibilities: either their ratio shall increase or it will decrease. It depends upon the thermophysical properties of refrigerants. some of the refrigerants, when they have wet compression, their COP is maximum, for example, ammonia or R22. Some of the refrigerants, when they are slightly superheated or saturated, their COP is maximum, for example, R134A or isobutane or propane. One more thing is done in actual practice. The vapor is not saturated in the form of saturated liquid here, it is subcooled. Subcooled to, let us say, C dash. When vapor is subcooled to C dash, the isenthalpic expansion shifts the points D to left, and this D point comes here D dash, and this increases the refrigerating effect without any increase in the consumption of work in the compressor. So, if we simply subcool the liquid instead of C, if we subcooled it up to here, we can increase the refrigerating effect. Now, this subcooling, how to attain this subcooling? As you know, in a refrigeration cycle, there are 4 components. One is compressor, where the vapor enters from evaporator, it goes to the compressor, from compressor it goes to the condenser, and from condenser it goes to the expansion valve. From expansion valve to the evaporator. If we depict this process on temperature entropy diagram, it is going to be like this. So, 1, 2, 3 and 4, and this is temperature T1 and this is temperature T2. Let us say T1 is equal to 40 degree centigrade and T2 is minus 20 degree centigrade, let us assume. So, the vapor coming from the evaporator is minus 20 degree centigrade, and vapor after condensation is at, it is saturated liquid at 40 degree centigrade. Now, if I exchange heat, I make an arrangement so that heat is exchanged between this and this, or through a heat exchanger, with the help of a heat exchanger, we manage to exchange heat between this. This is a cold temperature liquid which is coming at minus 20 degree centigrade, saturated. So, this low temperature refrigerant will pick heat from the high temperature refrigerant liquid which is at 40 degree centigrade, and it will get superheated. So, instead of minus 20, it may be at, let us say, minus 70, for example, minus 70 degree centigrade. So, the vapor will get superheated here. At the same time, heat, because this is saturated liquid and it is giving heat to the liquid at a lower temperature, the temperature of this may also go down. So, in the same process, we are superheating the vapor, at the same time we are subcooling the liquid. When we are superheating the vapor, the compression work is increasing. At the same time, when we are subcooling the liquid vapor, the refrigerating effect is also increasing. So, here also through this arrangement, the COP may not increase for some of the refrigerant, but definitely we are getting more refrigerating effect. We are getting more refrigerating effect with the same unit. Now, if I want to transfer these processes on pH diagram, let us take the processes one by one. Temperature entropy, superheating, saturated, then expansion. So, A, B, C, D. X is equal to 1, X is equal to 0. State 1, and this is 40 degree centigrade and this is minus 20 degree centigrade. Now, here at state 1 minus 20 degree centigrade, saturated vapor, we can directly take enthalpy from here. state B, 40 degree centigrade saturated vapor, but pressure is remaining constant. So, from this is state A, from state A will attain state B. So, this is a constant pressure line, this pressure line will be extended because the pressure is going to remain constant, and it is an isentropic process. So, there are constant entropy lines here. So, we will draw a line parallel to the constant entropy line, and that is how we will be getting state B. Now, after state B, the desuperheating will take place. In this process, the desuperheating will take place, and further removal of heat will bring the state C. State C will come here. Now, process C to D is constant enthalpy process. Constant enthalpy process because constant enthalpy lines are vertical lines. So, we will follow the vertical line here, and we will be getting state D. Now, second case, we can simply from here, if you want to find COP, simply HA minus HD divided by HB minus HA, we can directly take values from here, from this chart. Now, if the vapor is superheated, then these points will be shifted, and A will be here, somewhere here. Now, here if you want to show the superheating, pressure is constant, here the saturation temperature is minus 20 degree centigrade. Suppose the vapor is superheated by, let us say, 5 degree centigrade. So, this is constant temperature 0, 10, minus 20, this is minus 20 constant temperature line. This is 0 degree centigrade constant temperature line, this is minus 10 degree centigrade constant temperature line. So, A will be shifted somewhere here, and directly we can read enthalpy from this chart, and again we will follow the constant entropy line, and this is going to be the shifted point B dash. Similarly, when subcooling take place, if I say subcooling of 5 degree centigrade is taking place. So, here in this chart, first of all I will show it here. So, subcooling is taking place. So, here also in this chart, the temperature is 40 degree centigrade, this is constant temperature 40 degree centigrade line, this is constant temperature 30 degree centigrade line. So, now the temperature is 35. So, this is new point C dash. From this C dash, now expansion will take place, and this point D dash will attain. So, this is how we can transform all the processes in the temperature entropy diagram. Comfortably they can be transformed on pressure enthalpy diagram, and from these charts we can definitely find the COP relatively in an easier manner than in comparison to the case of temperature entropy diagram. Sorry, I have done a mistake here. This point C dash should not be here, point C dash should be here, because this is a constant pressure process. So, point C dash should be somewhere here, C dash on this constant pressure line. So, this is the point C dash, and then expansion of refrigerant take place. So, in a nutshell, if you want to transform the temperature entropy, the process on temperature entropy diagram, that is TS, A, B, C, D, sorry, this direction, this, and if the liquid is subcooled here and superheated here. So, if the vapor is superheated here, it will be like this, A will be shifted here, and if the liquid is subcooled here, we assume it to be along the liquid line, but actually it is somewhere here. It is compressed liquid, and expansion takes place like this. So, D point will be shifted here. Similarly, on pH diagram, on pH diagram, the A point, there are two pressures, lower pressure and higher pressure. The A will be somewhere here, A to B, isentropic compression, then desuperheating and cooling up to C, further subcooling by some degree centigrade, so C will be shifted here, and then expansion D. So, on pH diagram we are going to get A, B, C, D, and on this temperature entropy it is going to be A, B, C, D like this. Now, let us take one numerical example, R134A working between 40 degree centigrade and minus 20 degree centigrade, and the vapor is saturated before entering the compressor. So, vapor is saturated before entering the compressor, that is state A. Then state B, desuperheating, condensation, and then expansion, and then we get C, D, B1, and this is temperature. Here it is entropy. The direction of process is like this. This temperature is 40 degree centigrade, that is and this temperature is minus 20 degree centigrade. HA here again we can take directly from the properties table. Then HE is equal to again 386.55 kilojoules per kg. HC, enthalpy at C, it is equal to 256.41 kilojoules per kg. Enthalpy at D is equal to enthalpy at C. Enthalpy at D is equal to enthalpy at C. Enthalpy at B dash is also known to us, that is 419.43 kilojoules per kg. But for finding out the compressor work, refrigerating effect we can find HA minus HD. HA is here and HD is here. We have taken from properties table, but we do not have the value of HB. In order to find the enthalpy at B, we will use the relation SA is equal to SB. Entropy at A is equal to entropy at B. Entropy at A is known to us. Entropy at A is the entropy of saturated liquid at minus 20 degree centigrade, not saturated liquid, saturated vapor. So, that is 1.7413, 1.7413 kilojoules per kg Kelvin. Now, this entropy is equal to the entropy at B. We have entropy at B dash. This entropy at B dash is entropy of vapor at 40 degree centigrade, it is 1.7111 kilojoules per kg Kelvin. Now, what is the change in entropy from this point to this point? Now, change in entropy from this is a sort of sensible heating process. In this process, delta Q is equal to Cp delta T, Cp dt, and delta Q by T again divided by T. If you integrate this, that is change in entropy is equal to Cp natural log Tb by Tb dash, because it is from B dash to B, Tb by Tb dash. Now, Tb dash is with us, it is 40 degree centigrade. So, Tb dash is 40 degree centigrade or 313 Kelvin. The value of Cp at 40 degree centigrade vapor is 1.145 kilojoules per kg Kelvin. Change in entropy delta S is going to be equal to 1.145 natural log Tb by 313, and this change in entropy plus entropy at state B dash will give, if we add this delta S to entropy at B dash, the entropy at B dash is 1.7111 plus 1.145 natural log TB by 313. We will be getting entropy at A. Entropy at A is equal to 1.7413 kilojoules per kg Kelvin. If we solve this, and the value of TB is going to be equal to 321.4 Kelvin. Once we have the value of TB, we have the value of TB dash, that is 313.0 Kelvin. So, enthalpy at B dash plus, so enthalpy at B is equal to enthalpy at B dash plus Cp TB dash minus TB. It means the enthalpy at B is equal to enthalpy at B dash plus sensible heating, or Cp TB dash minus TB. So, enthalpy at B dash is 419.43 plus Cp is 1.145, TB dash is, sorry, it is TB minus TB dash. So, TB is 321.4 minus TB dash is 313. So, this, the value of HB is going to be equal to 429.05 kilojoules per kg. Now, we have the value of enthalpy at B and enthalpy at A as well. So, the compressor work is going to be equal to HB minus HA, and that is equal to 429.05 minus 386.55, and that is going to be equal to 42.50 kilojoules per kg. Right. Now, if you multiply this by mass flow rate, that is 1 kg per second, you will be getting 42.5 kilowatt of compressor work. The refrigerating effect is HA minus HC, and that is going to be equal to 386.55 minus 256.41, and that will give you 130.14 kilojoules per kg, because mass flow rate is 1 kg per second. So, if you multiply this by 1 kg per second, we will be getting 130.14 kilowatt. Now, COP of the system 130.14 divided by 42.50 is equal to 3.06. Now, if I want to use pH diagram for this, now in this pH diagram 40 degree centigrade. Now, vapor is saturated at the entry, vapor is saturated here. Now, vapor, that is state A. Now, vapor is compressed, it is isentropic compression, and the pressure in the condenser is constant. So, we will follow a line which we will follow the closest constant entropy line, and perhaps we will be getting a point B somewhere here, point B somewhere here. After B, the de-superheating will take place, we will get B dash here, then further cooling up to the liquid state, and then constant enthalpy expansion, C and D. Now, if we take the values from this pH diagram, and you can do it by yourself also as an exercise, and you will find that we are getting approximately the same value for refrigerating effect and coefficient of performance. Now, we have completed all the topics due for the today's lecture. Now, next lecture we will be taking vapor compression cycle, actual vapor compression cycle part 2.